Welcome to part 2 of episode 8 on Fourier and FFT concepts. In part 1, we covered time and frequency domains and showed examples of those using guitar waveforms. And we talked about how to interpret the FFT display. In this part 2 of episode 8, we're going to make good on using those concepts in circuit design. We're going to move from the concepts of phasor analysis that we met in episodes 6 and 7 to the more general concept of signal processing and filtering. For this particular filter, it's got a cutoff frequency of 1 kilohertz. And by the time you're out at 10 kilohertz, we're about 20 dB down, which is a factor of 0.1 in voltage. And of course, it rolls off even more at higher frequencies. Let's use what we used in part 1 to figure out what's going to happen at the output of this filter given a particular input waveform. So here's how we apply Fourier concepts in circuits. Let's say we have our guitar waveform, which I've shown over here on the left. We've learned that we can break that down into a bunch of sine waves and a possible DC offset. If our circuits are so-called linear circuits, which most analog circuits are, not all, but many are, and this filter certainly is, what we can do to find the output of the filter is examine what happens to each one of these components separately, as shown on the right. The fundamental frequency, the lowest one here, went through the filter, and the next one went through the filter, but it got decreased in amplitude by about 6 dB, or about a half in voltage. And then the higher harmonics, this looks like the third harmonic, got decreased even more. What the concept of linearity says is that we can take these individual guys, run them through the filter, and find out what the output is for each one, and then add them all up, and that will give us the result of what the filter does to the original waveform. And that is essentially the definition of a linear circuit. So this is admittedly a rather cumbersome looking view. We decomposed the original waveform using Fourier into components. We ran them all through the filter, and we added them all up at the output. This is a time domain view of what's going on. Let's switch to the frequency domain. In the frequency domain, we plot the magnitude of the spectrum of the input signal. To me, this is much simpler looking, and the operation is simpler too. We take this spectrum and we weight the different frequencies according to the response of the filter, which, remember, for this example, looks like this in decibels. So let's assume that our waveform has a fundamental frequency of, say, 1 kilohertz. So that component, the fundamental component sinusoid, is going to get reduced by 3 dB, which is a factor of about 0.707 or something. So it's going to be a little bit smaller, but not too much. The second harmonic would be out here at 2 kilohertz, and it's going to get reduced by 6 dB, and the third harmonic by even more, and so forth. And we can see the shape here in the box for a low-pass filter, echoing what we just looked at in detail there. So at the corner frequency here, we're down 3 dB, not very much, and you can see that this is maybe a little shorter than this one. That's what I tried to show. But the higher harmonics are out here in the so-called roll-off region, and the second harmonic, 2F0, is reduced by a significant amount, and 3F0 by even more. And sometimes this is all we really want to know. We don't necessarily have to reconstruct the waveform. That's a really important point. In exercises in school, we may have to do that, but in the real world, in design, we're interested in somewhat different things. In particular, one thing that we've scoped down to here is we're only showing magnitude plots, and I'll show you a reason for that in a second. Phase plots can also be important, but they're not done as much, mainly if wave shape matters. If you really do have to reconstruct the final output wave shape, then phase can be important as well. Indeed, in part number 1, we showed this display of the fast Fourier transform on our oscilloscope, and we made the statement that we often look at amplitude spectrum only. And why? Well, number one, it's the only thing, as far as I can tell, that this scope puts out. It doesn't even show you the phase spectrum. But that's not a good enough reason. The real reason has to be due to what's meaningful. And in music, of course, that's the frequencies we hear. But more than that, it's the tones and the harmonies. So how does our ear and brain extract that information from what's coming into the ear? And roughly what happens in the ear, specifically the inner ear, is that the organ there called the cochlea does essentially a Fourier analysis of the sound. So the sound wave coming in is a time domain waveform. But the information sent to the brain is the intensity of the different frequencies, just like the fast Fourier transform is showing us here. How is that done? Well, there's been a tremendous amount of research done to answer that question. And roughly speaking, people agree that there's what's called place coding going on in the human cochlea. So the time domain waveform, in the form of sound pressure level variations, strikes the eardrum, gets relayed through the series of bones, and contacts the cochlea, which is a fluid-filled spiral organ. So let's look at the bottom left here. Let's assume there's fluid inside this sac, and it spirals into a more narrow region at position A, whereas it's wider at position K. And all along this spiral, there are little hair cells that contact nerve fibers that go to the brain and tell it how strong things are at that region. So if I'm reading this graph properly over here, it looks like the lower frequencies are output at A, which is the most narrow region. That's interesting. And the higher frequencies are output most at the higher letters like H and I here. So as the time domain waveform moves the fluid along this path, different positions along the path respond to different frequencies. And all the different nerves along the path transmit their information to the brain. So the brain gets a mapping of frequency to which nerve cell is activated. So it's essentially getting a parallel readout of frequencies and amplitudes, just like the FFT gives us. Now, if you want to know more, do a search for something like place coding in the human cochlea. And it'll probably turn up this paper as well as many others. This paper, I want to point out, is a preprint, so it hasn't been peer reviewed. But there's been a tremendous amount of research in this area over the decades. And my understanding from looking at this paper and others is that this process only works to send amplitude information to the brain. I think it's encoded in how rapidly the nerves fire. That encodes the amplitude. But do some searches. Here's this paper. Or if you want some direct evidence that the ear doesn't generally respond to the relative phases of the different harmonics, you might bring up this video from our channel. Okay, let's get back to circuits. In episodes 3 and 4, we looked at a guitar amplifier circuit with the goal of understanding what all these different components are doing. When we plugged the guitar cable into one of these jacks, it shows up right here as a small voltage. And we discussed how C1 is a DC block to prevent any DC that might happen to be on here. There shouldn't be, but if there was, to prevent that from going into the next stage, which is this op-amp circuit. But along the way, there is a capacitor to ground. So if you look at R1 and that capacitor to ground, what does that look like? It looks like a low-pass filter. And then we talked about how this circuit here around IC1 is forming a voltage amplifier with a gain of, I think it was about 6. And so the output is here. And that's a low impedance output. That's going to be very important, as we're going to see. What happens next is it goes through this interesting circuit, and that's the one we're going to study today. And here's a block diagram we put together in episode 4 to summarize all the things I was just overviewing up here. There's a signal summer. If you have two signals coming in, they'll get added together. And then there's some amplitude protection and so forth. But our main concern now, going forward, is this audio response shaping block, which is right here. We know that if we have a small signal coming into the guitar amp, like this, it gets amplified by that op amp. And then it goes into this block, but what comes out? That's the question. Well, in those episodes, we already discussed that different frequencies are going to get attenuated by different amounts as they go through that circuitry. The question is, what do we get at the output here? And we're going to focus on how this audio response shaping block affects the spectrum as you move from this signal to whatever waveform is here. We don't really care what the waveform is because we now know that our ear's only interested in the amplitude response, but we need to know the spectrum at this point. Well, one way to answer that is to just do a quick circuit simulation. So here's the circuitry we're interested in. Remember, it's at the output of an op amp. And as we said in previous episodes, we can ignore the complexity of everything circuit-wise that's to the left of this point right here. Why? Because this is a low impedance output. It just looks like a voltage source. So that's my Vn here in this circuit simulation. So that signal goes into a parallel combination of R6 and C5, a resistor and a capacitor, which I just labeled R and C up here, but I put their values in. And the output goes to this resistor R8 and on to the rest of the circuitry. But notice R8 is 47K, so it's very big in comparison to these values. So essentially, this node is almost unloaded. So that means we can treat this as not being there. It's not going to load down the voltage or affect things very much at this point. So I only included this 1.5K to ground in my simulation. And I renamed it R1 for reasons that will become apparent shortly. Then I used LT-Spice to run a so-called AC analysis. And what the AC analysis parameters tell us is that we're going to sweep from 20 Hertz to 20 kilohertz with 10 steps per decade. And what does the response look like? Well, in dB, that's the solid red line, we have 0 dB. So the signal passes straight through this at high frequencies, but at low frequencies, it's attenuated. Why? Well, we learned in previous episodes that this capacitor is going to eventually become a so-called open circuit when its impedance gets much bigger than this resistor R. And that happens apparently somewhere below 100 Hertz. And at that point, we only have a resistive divider composed of R1 and R, and that produces about a 12 dB attenuation. So this is great if our interest was only in what this previously designed circuit is going to do to our waveform. But remember, we're interested in circuit design. We can mess around with the values here and probably come up with some interesting other variations on this. But that may not be the most efficient way to go about new designs. And that's why we study circuit analysis in school, or here on this channel, or watching other videos. This is a slide from episode 4 in this series. So if you want to know about this in detail, go back and review episode 4. There we said things like, well, at low frequency, what does that mean? Well, that's the question. Here we said much, much less than 340 Hertz, and that was gotten using the values here. But that doesn't tell us enough. We really need the complex math and voltage divider equation for a full solution, and that's where we're going next. Back in episodes 6 and 7, we already did a little bit of this. We looked at a somewhat simpler circuit, a simple low-pass filter, and we derived the so-called transfer function using complex math that was covered in episode 7, and phasors, which encode amplitude and phase of a sinusoid. And in phasor analysis, we just assume we kind of know what the frequency is. And in the case of this filter, we have different amplitude and phase responses at different frequencies. So if we know what the amplitude and phase of the source voltage is here, we can figure out what that amplitude and phase response is going to be and multiply these two complex numbers together and get the complex number, which is the output. And that encodes the magnitude and phase of the output sinusoid at that particular frequency. Well, what we're going to do now is generalize those concepts to putting spectrums here instead of simple phasors. And we're going to ask, how do we design a circuit that has a particular frequency response? How do we, for example, get some transfer function like this? Well, here's how we do it. Apologies for the very busy slide here. But this is what we need to go through to do and understand circuit design in detail. It's not too much different. It's just a little busy. But now it's less busy. We're going to take it a step at a time and reduce it into simplified blocks as we go. Then we will have to slog through a bunch of algebra, but I'm not going to drag you through it. I'll just walk you very quickly and show you the result. But to understand the circuit in enough detail to actually do design, here's what we need to do. First, we just look at it and recognize that R and C are in parallel, and that constitutes an impedance. It varies with frequency, and we're going to find out what the impedance is. But I put it as a block with Z next to it, the impedance. Z is the resistance R in parallel with the impedance of the capacitor. Now, once we figure out what that is, we can just use voltage divider to figure out what the output over input transfer function is. It's just going to be R1 divided by R1 plus Z. So it's really pretty easy when you look at it that way. But the algebra gets messy, so here we go. Z is R in parallel with the impedance of the capacitor. What's the impedance of the capacitor? Well, from previous episodes, we know it's 1 over J 2 pi FC. To make the algebra easier going forward, we're going to reduce that to 1 over J omega C, where omega is 2 pi F. You probably already know that. And you may know that sometimes people substitute J omega with a simple S. The reasons for that are multiple, having to do with things called Laplace transforms, but that's not what we're doing here. All we're doing here is we're just reducing the number of characters we have to write as we slog through the algebra. So Z sub C is 1 over SC. Later we can plug in S equals J omega 2 pi F to figure out the answer in the end. So R in parallel with 1 over SC is right here, because remember V out over Vn is R1 over R1 plus Z. So I substituted the expression for the parallel combination of R and Z sub C here in parentheses, the product over the sum. So this is a horrible compound fraction, looks gross, so I wanted to simplify it. And the first step on that long journey is to multiply top and bottom of this fraction in parentheses by SC. And when we do that, we get the expression on the right. I'll let you check that. But I'm going to check it too, because I always like to do that midway through a long algebraic path. So here's what we have so far for the transfer function, with, remember, S is J 2 pi F. So just think of S as the frequency, F. There's some other constants in it, but as F goes up, S goes up. So to do a quick sanity check, we can look at, for example, what happens when S tends to 0, i.e. when the frequency tends to 0. We know from looking at the circuit that the capacitor is going to become an open circuit, and we're just going to have a resistive voltage divider. Does that hold for this expression? Well, if S is 0 here, then this part goes away and we just have R over 1. So we have R1 over R1 plus R. There it is. We put the values in, 0.24, that's what we knew from before, so that seems okay. Likewise, when S or F goes to infinity, We have r over 1 plus infinity, which means everything in parentheses is 0, and the result is 1. That matches what we said in this slide, where C5 just couples the signal to the next stage. The signal goes right through the capacitor because we're at a high enough frequency. And we also confirmed that through simulation we have 0 dB there. So it looks like we're good up to this point. But we still don't know enough. We don't know what the frequencies of transition are. And that's what we're going to do next. To do design, we need to know what these corner frequencies are, where this starts going up and where it starts flattening out. So we're going to take the expression we have so far and modify it. We're going to do what's called putting the transfer function into a so-called standard form. And here's the algebra. I am not going to drag you through this. I'll just call your attention to this expression right here. We have, obviously, a voltage divider. That's good because we kind of expect that. And then what we have is what's called a ratio of polynomials in S. Now, there's only one capacitor in this circuit, so the polynomials are first order. If this was a much more complicated circuit with lots of capacitors as well as resistors, then we could have polynomials which are nth order in either the numerator, the denominator, or both. But we got to start somewhere, so we're using this circuit, and this is the result we have. What does it mean, and what is this omega sub z and omega sub p thing? Well, if you've studied some of this at university, you probably already know. But for those who haven't or those interested in a review, here it is. In all of that algebra, which involved a bunch of r's and c's, we just grouped them together and defined a new thing called omega sub z. And it's 1 over rc. That just comes out of the algebra. Likewise, omega sub p turned out to be 1 over r in parallel with r1, a quantity times c. Those are the so-called breakpoint frequencies in radians per second. To put them in hertz, we divide by 2 pi. And plugging the values in from our circuit here, we can compute that those breakpoint frequencies are 339 hertz and 1.4 kilohertz. Looking at our previous simulation, 339 or 340 hertz is about right here. And that's the point at which we've gone up 3 dB from what the asymptote is at low frequencies. So we're about 3 dB higher at 340 hertz. This is 100, 200, 300, so 340 would be about here. Likewise, 1.4 kilohertz is about here somewhere, and that's where we've reached almost the asymptotic 0 dB, but we're 3 dB below it. So this is the information we were looking for to do our design. We could now, for example, pick frequencies we want and solve for the R's and C values. And that's what design is. It allows us to go in that direction rather than just having it presented to us and ask what is the answer. Here we give specifications and we can solve for R's and C's. As a final check to make sure we got this right, let's take S and replace it by J 2 pi F and these expressions here and put them all together, and you should get this expression. And then we can take that expression and put it into Excel like we did back in previous episodes and plot the response. This is the magnitude of h of f. So I encoded this equation after taking magnitude. You can see the expression up here for one of the cells. And I got this curve. And then I asked Excel to change it to dB, and it gave me this. And this should match the simulation that I did earlier. At a higher level of design, we got to remember the application. Why are we doing this? Well, we have a guitar amplifier, and we want them to sell good, for example. So we want them to have a good tone by default. There are tone controls, but this seems to be some pre-shaping that goes on before messing around with tone controls. Let's see what it means in terms of spectrum. So I pulled out my trusty guitar here and I played an E note on the 4th string. And here's the waveform and here's the spectrum. And we'll notice that, like many guitars, it's very harmonic rich, but the fundamental and the 2nd and 3rd harmonic are dominant here. Now remember, this is a dB scale. There's 10 dB per vertical division here. And so, I don't know, can we kind of infer what we might hear? Probably not by looking at this graph alone. We need to remember this from episode 7. Sound pressure level is measured in pascals, but it's often quoted in dB. And more importantly, a 10 dB increase in level is perceived to be twice as loud. So that's important. What that means, for example, is that this 2nd harmonic is about twice as loud as this 3rd, 4th, 5th harmonic, and about 4 times as loud as this 12th harmonic out here. So these harmonics out here aren't going to contribute as much to what we perceive in the tonal quality as these fundamental 2nd and 3rd harmonics, for example. What if we want a brighter or richer sound in our guitar? Well, we might want to take some of these higher harmonics and boost them. Or equivalently, take the first 3 harmonics or first 3 or 4 and lower them, say by 10 or 15 dB. Well, that's precisely what this circuit does. It's a 12 dB bass cut or equivalently treble boost. And knowing the frequency of the fundamental, which in this case E on 4th string is 330 over 2. Remember, the E on the 1st string is 330 hertz, so we're 1 octave lower. So what is that, 165 hertz? And that is indeed the frequency of this first spectral line, about 160 hertz here. So that's no doubt what it went into the design of this circuit and the selection of the particular R and C values, giving us a response that looks like this. 165 hertz is about here, about negative 12 dB. And then the higher harmonics are out here. So they're going to be, relative to the fundamental, they'll be 12 dB higher now. And here's how we capture all those words and thoughts in some math. And some nice figures at the bottom. Now, note on these spectrums that I cut them off here. I cropped these images. That's because by the time you're down about 30 dB, you're not really hearing the stuff anymore. So it's only the first 20 or 30 dB of stuff that matters. And if you look at this response, this is the original signal. It looks like it's kind of sloping off like this for a best fit line. And then we go through our response shaping network, and now it looks somewhat like this. So we have indeed accentuated the higher frequencies, and in particular taken the fundamental and the 2nd harmonic and suppressed them a fair amount from what they were. How did I go from this to this? Well, here's the math for it. If you already know this, then you can skip ahead. There's some hopefully interesting material and filters coming up. But if you don't know this, this is really, really important. It has to do with something called adding dB. Remember that the output spectrum, V out of F, is equal to the transfer function times Vn of F. But if we put those things in the dB domain, since they're voltages, we take 20 log of the magnitudes of each one. So 20 log of the magnitude of V out is equal to 20 log of the magnitude of the product of H and Vn. Using rule of logarithm, you can get this second expression here. And then we note that this 20 log H of F is just H of F in dB. So that's this term. 20 log magnitude of V out is just magnitude of V out in dB volts. That's what the oscilloscope is showing us in the FFT domain. And likewise for the input in dB volts. So, at any frequency, what this expression says is, at any frequency, to get the dB volts at the output, we take the dB volts at the input and multiply by the transfer function. And whoops, no, we don't multiply. We add, because we're in the dB domain. So we add the dBs there. So it's really as simple as looking at the spectrum over here, noting where it is, and dropping it down 10 dB. So we would be here. And that's what I did. I actually just took this graph and covered up the first 12 dB of it. So you can check me to see if these look pretty reasonable to you. But that's what this is doing. It's basically subtracting dBs in the lower frequency domain, according to this expression. And final thing of note on this slide, before we had just phasors here, but now we can put the whole spectrum there, V in of F and V out of F. V out of F being H of F times V in of F. So we now just put spectrums where we had just phasors before. Okay, that brings us to the end of this episode, except that I do have a little bit more here if you want, but I think you'll find this material pretty interesting. We talk about analog and digital filters. This really deserves a future video, or many future videos probably, but I'm going to give you an introduction to it that I hope will enable you to understand and possibly even begin to work with these things. Other possible future videos you can see here. These are notes from when I taught the Electronics 2 course at university. And I just want to overview them real quick with the most important things. So what you'll learn in electronics courses are many, many things. And sometimes people will concentrate on operational amplifiers and building filters with those. And these two sheets showed what we covered in that course. 4 filters built with operational amplifiers. So when I began this material, I began it with this as part of the lecture. Typical op-amp applications. Use as a signal preamp / conditioning between a transducer like a microphone and an analog to digital converter. And then, as you probably know, we do pretty much everything else using digital signal processing. So this diagram says we've got about a 10 millivolt signal-ish peak amplitude coming out of a microphone. Here it looks like a sine wave, but I've drawn some stuff all over it. That's like the high frequency noise we talked about in a previous episode that you often see on oscilloscopes from microphones these days, if you ever try that. In any case, 10 millivolts is too low to go directly into an analog to digital converter, so we have to amplify it. And along the way, we use low-pass filters for a couple of reasons. One is to get rid of that high-frequency noise, and another one is for what we call anti-aliasing. And what the analog to digital converter does is it samples the voltage. Now remember, this is a so-called continuous time waveform. So at any given time t, you have a value here, and you can finally divide times up as much as you want. But we sample the thing at particular times, which is based on the so-called sample rate. And what we get out of the ADC are a bunch of numbers like this. And this, you can probably see, looks like a sine wave. So I got rid of the noise, but I digitized this sine wave after the low-pass filter, and I get out a bunch of numbers that basically map out a sine wave. And then through the magic of digital signal processing, we can do the same thing we do in the analog domain with filters and S domain and so forth. We can do that in the digital domain. I'm not going to cover that here because it's a huge topic, but I will show you a video right at the end. In any case, you could modify this, shape its frequency response, for example, just like you do in the analog domain. And then you take that and feed it to a digital to analog converter. And then we need a low-pass filter after that for various reasons, or it's just implicit in the amplification. And then we go into an audio power amp and a speaker. And if you want to think about that in more depth and see a little video that shows it in practice, this is a video I put together for the electronics course, I guess 11 years ago, where I was using an Arduino, a very underpowered one relative to today's Arduinos, to do a little digital signal processing demonstration. And what was implemented in the code, which you can see in the upper right, a snippet of it, what was implemented in that code is a simple low-pass filter. I think it was about 100 hertz because I couldn't get the sample rate above 8 kilohertz for this thing. So these are very low-frequency waveforms. This is the input waveform to the ADC. This is the output of that filter. And here we're below the corner frequency. Notice the little stair steps here. That's because we're using a simple 5-bit resistor digital to analog converter. Because for whatever reason, the Arduinos didn't have digital analog converters in them. They have ADCs, but not DACs. Anyway, so you can see the quantization levels. You can also see these spikes. That has to do with how I was outputting to these resistors individually so they don't time align perfectly. In any case, this is below the corner frequency of the low-pass filter, and then as you crank up the frequency of the input signal, as shown here, you can see that the amplitude is decreasing to relative to what it was. So it is a low-pass filter. And that video will talk you through a number of other items, especially the aliasing issue. It's kind of really interesting to see. So I'd encourage you to search YouTube for this, or I'll see if I can put this in the description, but here's the link to it. And it's important to note that the theory of how you do signal processing in the so-called discrete time domain, these digitized signals, is a little bit more difficult. I don't know. It's a little bit different than the analog stuff we've been talking about. The actual implementation is very simple. Here's the computation of the new output at each sample, and we just read the input, perform this little computation, which says that the new output at sample point n is equal to the new input at that sample point plus 0.875 times the old output. And that's all you need to create a low-pass filter, something like that. So not much code. It does need to run fast. Now, this video does not show this code, but there is another video on the channel called Arduino Reverb that does show some code. So you can see how it's implemented. This is an Arduino Due, which I don't think is even sold anymore, but it gives you a flavor for how you can do some of this stuff using Arduinos. If you want to learn more, here's some ways. Videos and websites. There's a playlist that this video is contained in, the ECE Topics playlist, and the channel has a number of playlists as well beyond this. Of course, many other excellent videos out on YouTube, so search and sample those. If you want slides for this episode or any of the others on our channel, they're at ecefiles.org. And of course, do Google searches for things. Here's a couple of books. This is a nice one if you want a kind of a cookbook approach to doing filters, but it also covers circuits in general very well. Lots of good diagrams. If you're at university and you've had some of this material before, I brought down the Shawm's outline when I was making this video. Pretty inexpensive on Amazon. And of course, all this material is covered in depth in university courses. So linear systems is where some of this material is from. I taught that a long time ago. And some of it was from the electronics courses and the intro to electrical engineering courses and so forth. So that's finally the end. If you got this far, thank you for sticking with us and for watching the video, and I hope it's been useful to you. I try to make these things a little bit different than what's out there on other videos on YouTube. I tried to emphasize some of the things I've learned and relied on over a 40-plus year work in design and education. All right, thanks for watching. Bye.